You know, if you've ever driven past a major chemical refinery at night, or maybe seen footage of an offshore oil rig out in the dark ocean, you've definitely seen it,
Oh yeah, the Fuller stack.
right? There's usually this giant, towering pipe, and at the very top, just this massive, roaring plume of fire burning endlessly into the night sky.
It is a very dramatic image, honestly. Visually, I mean, it's almost cinematic, like something straight out of Blade Runner.
Totally.
But, when you look at it from a chemical engineering perspective or even just an economic one, it is an absolute tragedy.
A complete tragedy, because you are literally watching them burn money. I mean, that flame is stranded natural gas.
Exactly.
It's methane that they've pulled out of the Earth's crust along with the crude oil they were actually looking for. But because that rig is like in the middle of nowhere or sitting off the coast of Trinidad.
Or deep in the Alaskan wilderness, right?
Yeah, where there is zero pipeline infrastructure, the engineers just have no economically viable way to transport it to market. You can't just put a gas in an open bucket and put it on a cargo ship.
Right, you really can't.
So they just ignite it. They burn it off simply to get rid of it.
And we are talking about staggering volumes of energy here. Stranded natural gas makes up a massive portion of our global energy reserves. It's quite literally everywhere.
It really is.
But moving a gas requires either multi-billion-dollar continent-spanning pipelines or these massive cryogenic liquefaction plants.
To ship it as liquefied natural gas, or LNG.
Right, and to do that, you have to cool that methane down to like negative 260 degrees Fahrenheit so it condenses into a liquid.
Which is insane.
It is. That requires highly specialized, heavily insulated tanker ships. So in many remote locations, neither the pipeline nor the cryogenic option is even remotely feasible. The map just doesn't work.
Which is exactly why we are pulling out the heavy material for you today. We are taking a depth dive into what is arguably one of the most challenging, consequential, and, honestly, financially lucrative topics in all of modern industrial chemistry.
Natural gas conversion.
Exactly. The holy grail here, the thing that every major energy company on Earth has spent billions trying to perfect, is figuring out how to break the incredibly stubborn carbon-hydrogen bonds in methane and stitch those molecules back together into transportable, highly valuable liquid fuels right there at the source.
Because if you can turn that gas into a stable liquid at room temperature, you don't need a cryogenic ship.
Right.
You just need a standard oil tanker.
Yeah.
If we connect this to the bigger picture, if you understand the mechanics of this conversion process, you unlock the underlying realities of global energy economics.
Absolutely.
You see the future of synthetic fuels, and you understand the very foundation of modern petrochemicals.
Yeah.
Everything around us, from the plastics we use to the fuel in our heavy transport, it all traces back to this specific chemical hurdle.
So, to guide us through this, we're diving deep into a massive grounding text. We are looking at Natural Gas Conversion 6, which is the peer-reviewed proceedings of the 6th Natural Gas Conversion Symposium held in Girdwood, Alaska, back in 2001.
A classic.
Yeah. Now, I know what you might be thinking. A 2-decade-old book of industrial chemistry symposium papers.
Sounds a bit dry, right?
Right. But this text is widely considered the foundational bedrock of the modern gas-to-liquids industry. It captures the exact moment when the theoretical pipe dreams of the 20th century, things chemists had been sketching on chalkboards for decades, finally started colliding with heavy industrial reality.
It's a remarkable snapshot, really, of a technological pivot. The papers in this compendium outline the fundamental physics, the catalytic chemistry, and the economic hurdles that every single modern energy company is still wrestling with today.
Because the physics haven't changed?
Exactly. The laws of thermodynamics haven't changed since 2001. The physical barriers discussed in these papers are the exact same barriers preventing a completely seamless transition to alternative fuels right now.
Okay, let's unpack this. Because to really grasp the sheer scale of the engineering here, we have to start at the molecular level. We have to start with the methane molecule itself.
Right, one carbon atom surrounded by 4 hydrogen atoms.
And the problem is that those bonds are incredibly strong. Methane is thermodynamically stable. It just doesn't want to change into anything else unless you absolutely force it.
It's stubborn.
Super stubborn. And the first major hurdle the symposium tackles, chapter 1 essentially, is simply tearing that molecule apart. They call it the synthesis gas, or syngas challenge. Let's do a quick big idea here. Producing the syngas is the most capital-intensive step in the whole process, but these new millisecond reactors offer a crazy miniature alternative.
Yes, producing synthesis gas is the fundamental bottleneck. Syngas is simply a mixture of hydrogen gas and carbon monoxide.
Okay.
You can think of it as the intermediate clay from which almost all synthetic chemicals and liquid fuels are sculpted. You cannot easily turn methane directly into a complex liquid like diesel fuel.
You have to break it down first.
Right. You first have to blast the methane apart into individual carbon, hydrogen, and oxygen atoms. That is your syngas. Only then can you begin to reassemble them.
And the economic reality presented in the text is brutal. Generating the syngas accounts for roughly 60% of the total capital cost of a gas-to-liquids plant.
60%. It's massive.
Before you've even made a single drop of usable liquid fuel, you've spent more than half your multi-billion-dollar budget just breaking the methane apart. And historically, the way we've done that is through a process called steam methane reforming, or SMR.
Which is an absolute beast of a process.
Yeah, when I picture an SMR plant, I imagine this giant brute force industrial cathedral of fire.
That is a very accurate visual, actually. Steam reforming is a highly endothermic process.
Meaning it absorbs heat. Right?
Yes. Endothermic, meaning it requires a massive continuous input of external heat just to keep the chemical reaction going. The way an SMR plant works is you mix the methane gas with high-pressure steam, and you pump that mixture through these colossal multi-story tube furnaces.
It's huge towers of fire.
Exactly. These tubes are packed with nickel catalysts, and the entire environment has to be maintained at around 900 degrees Celsius under very high pressures.
And because you have to constantly push all that thermal energy through the thick metal walls of the tubes to reach the gas inside, the physical footprint of the plant has to be enormous.
You need massive burners.
Massive heat exchangers, thousands of linear feet of specialized alloy piping. It is an infrastructure nightmare, especially if you're trying to build this on a remote offshore oil rig. You just don't have the space.
You're touching on the core issue there. SMR is highly efficient at scale, but it cannot be miniaturized effectively. Furthermore, the chemistry of reacting methane with steam inherently produces a syngas mixture with a hydrogen-to-carbon monoxide ratio of 3:1.
3 parts hydrogen, 1 part carbon monoxide.
Right. You end up with way too much hydrogen.
Which is a huge problem because, as we'll see later when we try to make synthetic diesel, the chemistry actually demands a ratio of 2:1. So SMR leaves you with all this extra hydrogen, which you then have to separate and deal with, adding even more equipment and cost. So the text introduces the alternative that everyone was obsessed with at the symposium: Catalytic Partial Oxidation of Methane, or POM.
Partial oxidation takes a completely different thermodynamic approach. Instead of reacting the methane with water in the form of steam, you react it directly with a carefully limited amount of pure oxygen.
Okay.
Unlike steam reforming, this reaction is mildly exothermic. It actually generates its own heat.
Oh, wow. So it's autothermal.
Precisely. Once you initiate the reaction, it sustains itself without you having to constantly burn fuel to pump external fire into a massive furnace.
Yeah.
And crucially, partial oxidation naturally produces that highly desirable hydrogen-to-carbon monoxide ratio of 2:1.
So partial oxidation sounds like an absolute slam dunk. It gives you the exact chemical ratio you want, and it generates its own heat. But here is where we get to the work of L.D. Schmidt, detailed heavily in the text, and this mind-blowing concept of millisecond contact time reactors. This is where the physics shift from standard industrial engineering into something that is just totally wild. Walk us through what is actually happening inside one of Schmidt's reactors.
Well, Schmidt's work focuses on moving away from massive packed beds of catalyst pellets and instead using monolithic catalysts.
Monolithic, like a solid block.
More like a highly porous, intricate ceramic foam. Imagine something that almost looks like a rigid metallic sponge. This ceramic foam is coated with a microscopic layer of noble metal, typically rhodium.
Okay, rhodium sponge. Got it.
And instead of a furnace the size of a 10-story building, the actual reaction zone in this setup might be the size of a coffee cup. You shoot a pre-mixed stream of methane and oxygen gas through this foam at astonishing velocities, around 1 meter per second.
Wait, 1 meter per second through a dense foam.
Yes. Because the gas is moving so incredibly fast and the catalyst layer is so thin, the total time the gas spends in physical contact with the active rhodium, what we call the residence time, is roughly 1 millisecond.
1,000th of a second.
1,000th of a second.
That is absurdly fast. It is almost difficult to comprehend chemistry happening on that timescale.
It really challenges our conventional understanding of industrial kinetics. And the thermal gradients inside that coffee cup-sized reactor are extreme.
How extreme?
Well, the pre-mixed gas enters the ceramic foam at roughly room temperature. Within that single millisecond, and within a physical distance of maybe 1 millimeter inside the foam, The violently exothermic reaction heats the gas and the catalyst matrix to 1,000 degrees Celsius.
What?
Yeah, we're talking about heating gradients of 1,000,000 Kelvin per second and spatial gradients of 100,000 Kelvin per centimeter.
Okay, I have to push back here, or at least ask for a mechanical clarification. You are taking a highly explosive mixture of methane and pure oxygen. You are flowing it at high speed into a ceramic block, and it is instantly heating to 1,000 degrees Celsius.
Right.
How does this actually work without just causing a catastrophic localized explosion? I mean, why doesn't the methane just instantly burn up into carbon dioxide and water? How are you perfectly stopping the reaction halfway at carbon monoxide and hydrogen?
That specific question, how the syngas actually forms in that single millisecond without detonating, is one of the most hotly debated topics in the symposium text.
I can imagine.
There are two competing schools of thought. The first is the direct mechanism. This theory suggests that the methane and oxygen molecules hit the rhodium catalyst and, through a complex surface interaction, magically and directly rearrange themselves into carbon monoxide and hydrogen, bypassing total combustion entirely.
It assumes the rhodium acts like a perfect traffic cop, directing the atoms exactly where they need to go before they even have a chance to just burn. But what is the second theory?
The indirect mechanism.
Yeah.
And this theory argues that what you just described, the instantaneous explosion, absolutely does happen.
Oh, wow.
According to the indirect model, the moment the methane and oxygen hit the very front edge of the catalyst foam, they instantly, totally combust into carbon dioxide and water vapor. This violent combustion releases a massive amount of heat.
Okay, so it does explode.
It does. However, because the engineers strictly limited the amount of oxygen in the initial mixture, all of the available oxygen is entirely consumed in that first fraction of a millimeter.
Okay, so the front edge of the reactor is basically a raging fire.
Exactly. It's a highly exothermic combustion zone. But the remaining unburned methane gas, which is now traveling incredibly fast alongside this newly formed carbon dioxide, water vapor, and intense heat, moves a millimeter deeper into the catalyst.
And there's no oxygen left.
None. So at this point, lacking any free oxygen to burn, the methane is forced to react with the carbon dioxide and water in an endothermic reforming reaction. That secondary reaction absorbs the heat generated by the front edge and produces the carbon monoxide and hydrogen we want.
That is fascinating. So the indirect mechanism suggests that this tiny coffee cup-sized monolithic reactor is essentially a microscopic version of a massive SMR plant.
That's a great way to put it.
The front millimeter of the catalyst acts as the fire, providing the intense heat, and the next millimeter of the catalyst acts as the reforming tube doing the chemical work.
Precisely the way to visualize it.
Yeah.
But you can imagine the incredibly complex heat management issues this creates within the physical structure of the ceramic foam.
Oh, definitely.
You have an initial microscopic zone that is generating so much heat it wants to melt the rhodium, followed immediately by a microscopic zone that is absorbing so much heat it wants to freeze the reaction entirely. It's like trying to keep a match lit inside a hurricane while simultaneously trying to freeze the smoke.
That sounds impossible. And wait, isn't the rhodium catalyst supposed to be carefully guiding all this chemistry? If things are this violent, is the metal actually in control?
Not entirely, no. And that is a crucial nuance that L.D. Schmidt points out in his research. At 1,000 degrees Celsius, the rhodium catalyst initiates the primary reactions. But at those extreme temperatures, homogeneous gas phase reactions begin to take over.
By gas phase, you mean reactions happening in the empty void space inside the pores of the foam, completely detached from the metal surface itself.
Yes. The thermal energy is so high that the molecules just start tearing each other apart in the gas phase. These are violent, free radical chain reactions.
Which sounds dangerous.
It is. This is where the engineering tightrope walk becomes terrifying. If your gas flow rate isn't perfectly tuned down to the microsecond, or if your operating pressure changes even slightly, these gas phase free radicals can suddenly cascade out of control.
What happens then?
This can lead to unwanted open flames shooting through the reactor, or, even worse, the sudden dumping of solid carbon soot, what chemists call coke.
Oh, coke.
Right. If the reactor cokes up, the solid carbon instantly plugs the microscopic pores of the ceramic foam. The pressure spikes, and the reactor literally destroys itself.
It's an incredible balancing act, and it makes me wonder about the real-world application because, natural gas isn't just pure laboratory-grade methane.
Not at all.
If you pull it out of the ground in Alaska, it contains heavier alkanes. You have ethane, propane, butane mixed in. How does the presence of those heavier, highly reactive, easily ignitable gases complicate this incredibly precise millisecond heat balance?
It complicates it immensely. Higher alkanes like ethane and propane have much weaker carbon-carbon bonds compared to methane's carbon-hydrogen bonds.
So they burn faster.
They ignite faster, they burn hotter, and they are notorious for instantly forming that solid carbon coke we just discussed. In a commercial setting, if a slug of propane-rich gas hits a millisecond reactor tuned for pure methane, the localized heat generation in that first millimeter of the catalyst would spike massively.
It's melting the whole thing.
Potentially melting the ceramic substrate, yes. Commercializing these partial oxidation reactors requires incredibly robust pretreatment of the natural gas or catalyst formulations that can dynamically absorb those thermal shocks without degrading. It is a brilliant theoretical solution that encounters brutal realities in the field.
Okay, before we move on, let's do a quick practical recap of this first chapter. So, syngas generation is about 60% of the capital cost in these plants.
Right.
Partial oxidation in these crazy millisecond reactors gets you over 90% conversion almost instantly. But you have to perfectly balance extreme hot and cold zones to stop it from melting or coking up.
That sums it up perfectly.
And for you listening, here is a critical thinking challenge to mull over. If a millisecond reactor can replace a massive furnace, what are the actual safety risks of running an autothermal process at 1,000 degrees with highly explosive gas mixtures on an isolated oil rig?
It's a scary thought.
It really is. Okay, so let's say the engineers pull it off. They manage the ethane, they perfectly balance the thermal gradients, and they successfully, miraculously generate this perfect 2-to-1 syngas in a tiny millisecond reactor.
A huge achievement.
We have achieved the first step, but syngas is just an intermediate. It's a highly toxic, invisible gas. If you put it in the fuel tank of a diesel truck, the truck isn't going anywhere.
Obviously not.
So now that we have these basic building blocks, the chemistry has to completely shift gears. We have to go from tearing molecules apart to carefully stitching them back together into long, complex liquid hydrocarbons. And that sets up the next major hurdle the symposium addresses. Chapter 2, Fischer-Tropsch synthesis. The big idea here is that this process acts like molecular Lego, but controlling the exact size of the Lego block you build is a massive headache.
Indeed. Fischer-Tropsch synthesis is essentially molecular Lego. It is the process of taking those simple syngas molecules, the carbon monoxide and hydrogen, and polymerizing them, chaining them together, carbon by carbon, into valuable liquid fuels.
And these fuels are super clean, right?
It's very clean. One of the great advantages of this process is that the resulting fuels are completely free of sulfur and aromatic compounds, making them incredibly clean burning compared to crude oil derivatives. However, as you mentioned, the chemistry of controlling the exact length of these molecular chains remains a massive, ongoing engineering hurdle.
So we have our syngas mixture, we pump it into a Fischer-Tropsch reactor. Let's get down to the atomic level. What is actually doing the stitching? How do these gases turn into a liquid?
The heavy lifting is done entirely by the catalyst. The syngas molecules physically adsorb, meaning they stick to the surface of a metal catalyst.
Okay.
Once on the surface, the carbon-oxygen bond of the carbon monoxide is broken, the oxygen is ejected, and the remaining carbon atom begins to bond with the hydrogen atoms and neighboring carbon atoms, growing a hydrocarbon chain directly on the metal surface.
Like beads on a string.
Exactly.
Yeah.
And in the world of Fischer-Tropsch, there is a legendary century-old heavyweight battle between two primary catalytic metals, cobalt and iron. Choosing between these two metals dictates the entire physical architecture and economics of your plant.
Let's look at the tail of the tape here. Cobalt versus iron. Why choose one over the other?
Well, cobalt is highly active, meaning it drives the reaction very quickly, and it has a very long operational life before it degrades. But most importantly for our context, cobalt strongly prefers to consume syngas at a strict ratio of 2 parts hydrogen to 1 part carbon monoxide.
Oh, wait. If you recall our discussion on partial oxidation, that is the exact ratio produced by the advanced conversion of natural gas.
Bingo. So for natural gas to liquids processes, cobalt is the undisputed, highly efficient champion.
But cobalt is also a relatively rare and incredibly expensive transition metal. What about iron? I assume iron is drastically cheaper to procure at an industrial scale.
Iron is essentially dirt cheap compared to cobalt, but it behaves fundamentally differently on a chemical level. Iron has a very high intrinsic activity for something called the water-gas shift reaction.
Let's break that down. What exactly is the water-gas shift reaction and why does it matter here?
The water-gas shift reaction is a secondary chemical process where carbon monoxide reacts with water vapor to produce carbon dioxide and hydrogen gas.
Okay.
Now imagine you were trying to make liquid fuels, but instead of starting with natural gas, you were starting with coal. If you gasify coal to make syngas, because coal is mostly carbon and has very little hydrogen, the resulting syngas is severely starved of hydrogen. It might have a ratio of 1 part hydrogen to 1 part carbon monoxide.
Which is useless for cobalt because cobalt demands that 2-to-1 ratio to build the liquid fuels.
Exactly. But if you feed that hydrogen-starved coal gas to an iron catalyst, the iron will actually perform the water-gas shift reaction while it is building the fuel chains.
Oh, that's clever.
It will take some of the carbon monoxide, react it with the water floating around inside the reactor, and autonomously generate its own extra hydrogen to make up the deficit. It chemically balances its own feed stream.
Wow.
It is brilliant for coal-derived syngas, which is why it was used extensively in places like South Africa. The downside, however, is that a huge amount of your valuable carbon ends up being rejected as carbon dioxide gas, rather than going into your liquid fuel.
Okay, you mentioned water floating around inside the reactor. That brings up a major point of contention in the symposium papers. Where is that water coming from?
Water is a natural, unavoidable byproduct of the Fischer-Tropsch polymerization reaction itself. Every single time the catalyst links a new carbon atom to the growing hydrocarbon chain, it has to reject the oxygen atom that came in with the carbon monoxide.
Right.
That oxygen atom immediately grabs 2 hydrogen atoms and forms a molecule of H2O. So the more liquid fuel you make, the more water you are simultaneously generating right there on the catalyst surface.
And how does all that highly pressurized, superheated water impact our expensive champion, cobalt?
Negatively, very negatively. High localized concentrations of water vapor can oxidize the surface of the cobalt, physically altering its crystal structure and permanently deactivating the catalyst.
That sounds like a disaster for the plant.
It is. And this chemical vulnerability becomes a severe engineering paradox when we look at how these massive commercial reactors are actually built today. The text spends a lot of time detailing the shift away from simple tubes and towards something called slurry bubble column reactors, or SBCRs.
Give us a visual of a slurry bubble column reactor. When I hear slurry, I think of wet cement.
It's not far off. Imagine a massive vertically oriented steel silo, perhaps several stories tall. Inside the silo is a churning, violently boiling liquid bath of heavy, long-chain hydrocarbon wax.
Wax?
Yeah, it's essentially a vat of molten candle wax. Suspended throughout this boiling liquid wax are billions of microscopic powdered particles of your cobalt catalyst. You take your syngas and you vigorously bubble it up from the very bottom of the silo.
So the gas bubbles rise up through the molten wax?
Yes, and as the bubbles rise, the syngas dissolves into the liquid wax, physically diffuses across the liquid, finds a suspended solid particle of cobalt catalyst, reacts on the surface, and the new liquid hydrocarbon products that are formed just shed off the catalyst and add to the total volume of the liquid bath.
That sounds incredibly chaotic. You have gas bubbles, a boiling liquid phase, and a solid powder phase all mixing violently. Why would engineers choose something so messy compared to just packing a stationary pipe with catalyst pellets and blowing the gas through it?
Because of the thermodynamic realities of the heat, Fischer-Tropsch synthesis is violently exothermic. The polymerization reaction releases massive amounts of thermal energy.
Okay.
If you use a stationary fixed bed of catalyst packed in a tube, the heat cannot escape fast enough. You get localized hotspots. The temperature spikes, the catalyst begins to uncontrollably crack the molecules into methane gas, and eventually the catalyst simply destroys itself.
So the wax is a coolant.
Yes, exactly. The churning liquid wax in a slurry reactor acts as a massive dynamic thermal sponge. The constant boiling and mixing absorb the heat generated by the microscopic catalyst particles and distribute it perfectly evenly throughout the entire massive volume of the reactor. The temperature remains stable everywhere.
It's an elegant solution to the heat problem. But wait, if it's a giant churning vat of liquid, there has to be a massive amount of backmixing.
Oh, yeah.
In a normal pipe, the water vapor you generate would just get swept out the back end by the gas flow. But in a boiling cauldron of wax, the water doesn't just leave. It gets trapped, mixed back down, and churned repeatedly into the slurry.
That's the problem.
So you're utilizing the absolute best, most economically viable reactor design for heat management, but it inherently traps the very water that poisons your incredibly expensive cobalt catalyst.
That is the exact paradox the chemical engineers are fighting, and it is documented extensively in the text. You have to carefully, mathematically tune the pressure, the overall operating temperature, and the upward velocity of the syngas bubbles to try and strip that water vapor out of the top of the slurry column before it can accumulate and permanently degrade the cobalt. It is a constant battle between optimizing heat transfer and preventing catalyst oxidation.
Okay, let's unpack the actual liquids coming out of this process, because here is where the chemistry gets really frustrating. The goal of all this billion-dollar infrastructure is usually to make synthetic diesel fuel.
Right.
Diesel is roughly a chain of 10 to 20 carbon atoms linked together. Here's where it gets really interesting. This cobalt catalyst sitting in the wax doesn't just cleanly produce perfectly uniform 20 carbon chains, does it?
No, it absolutely does not. The product distribution, meaning the lengths of the hydrocarbon chains that come off the catalyst, is strictly governed by a mathematical model known as Schultz-Flory-Anderson kinetics, or the SFA distribution.
SFA distribution.
Yes. It is essentially an immutable statistical probability curve dictated by the laws of physical chemistry.
I always visualize the SFA distribution like flipping coins or rolling dice at a casino. Say you want to build a chain of exactly 15 carbon atoms to make high-grade diesel. At every single microscopic step of building that chain, the cobalt catalyst essentially flips a coin.
I like that analogy.
Heads, it grabs another carbon atom from the syngas and adds it to the chain, growing it by one. Tails, it stops the reaction, releases the molecule into the wax, and starts building a brand new chain from scratch.
That is a highly effective way to explain it.
So to get your perfectly sized 15 carbon chain, you need that catalyst to flip heads exactly 15 times in a row, and then flip tails on the 16th try.
Which is statistically unlikely to happen every time.
Exactly. Because it is pure statistical probability happening trillions of times a second, you are inevitably going to get a massive amount of single carbon molecules, methane gas, where the catalyst flip tails on the very first try.
Right.
And simultaneously, you're going to get massive, heavy, 100-carbon solid waxes where the catalyst just kept flipping heads 50, 60, 70 times in a row.
That is the reality of the SFA distribution. Nature simply will not allow you to selectively produce only the middle-length chains you desire. You are thermodynamically forced to produce a wide, non-selective spectrum of molecules, ranging from virtually useless light hydrocarbon gases all the way to heavy solid paraffin waxes that look like opaque blocks of plastic.
So why can't we cheat? Chemists are famous for hacking thermodynamics. The source text has an entire section dedicated to testing bifunctional catalysts. Why can't we just take our Fischer-Tropsch cobalt powder and mix it directly with the zeolite?
Well, let's define a zeolite for clarity first.
Right. A zeolite is basically a crystalline mineral structure that acts as a microscopic molecular sieve. It has tiny, precisely sized pores, and those pores are highly acidic. In oil refining, zeolites are used to crack large molecules into smaller ones. The large molecule enters the pore, the acid attacks the bonds, and it breaks in half. So why not put a zeolite right next to the cobalt? Let the cobalt flip the coins and build the chain, but the moment that chain gets longer than 20 carbons, it bumps into the zeolite, the acid attacks it, and it cracked it right back down into the diesel range. It seems like a foolproof way to stop the heavy waxes from forming.
It is a brilliant idea in theory, and many research groups in the symposium attempted it. But the empirical data in the text shows exactly why it fails economically.
Why does it fail?
Zeolites certainly do what you described. They lower the probability of infinite chain growth, effectively stopping the heavy waxes from forming. But the acidic cracking mechanism of the zeolite is simply too aggressive. While it cracks the large chains, it also indiscriminately attacks the medium-length chains you actually want.
Oh, no.
Yeah. It ends up dramatically increasing the amount of C1 to C4-like gases produced, methane, ethane, propane. You end up losing a massive fraction of your highly valuable carbon into cheap, unliquefiable gas that you can't put on a ship.
You solve the wax problem but create a gas problem. So if we can't use zeolites to cheat the SFA distribution, how do we hack the system?
The symposium papers explore a fascinating operational hack known as periodic pulsed operation. Instead of providing a steady, continuous flow of syngas to the catalyst, the engineers pulse the feed. They rapidly cycle the partial pressures of the carbon monoxide and hydrogen inside the reactor.
Like revving the engine instead of holding a steady speed.
Exactly. The theory is that by dramatically pulsing the reactant concentrations, you alter the surface chemistry dynamically. You can literally force the growing hydrocarbon chains to detach from the catalyst surface prematurely.
Just shake them off.
Basically, you wait until the statistical average of the chains reaches the C10 to C20 length, and then you pulse the system, forcing a mass detachment. It is an attempt to use kinetic shock waves to bypass the natural statistical limits of the SFA curve, thereby maximizing the yield of diesel and minimizing the wax.
That is incredibly clever. It's using fluid dynamics and pressure to outsmart physical chemistry. Let's do a quick practical recap of this Fischer-Tropsch chapter. So, cobalt is best for natural gas, iron is cheaper but handles water differently, slurry reactors manage the crazy heat but trap the water, and we are stuck with the SFA distribution, meaning we always make heavy wax and light gases alongside our diesel.
Exactly right.
And for a critical thinking challenge, given those SFA limits, how would you design a plant to ensure absolute zero waste of those heavy wax and light gas byproducts? It's a tough puzzle, but it also highlights the sheer difficulty of this entire Fischer-Tropsch process.
It really does.
Think about what we are doing here. We are using massive amounts of heat to rip methane apart. Then we are using giant, high-pressure towers of violently boiling wax and rare metals to force those fragments back together, fighting statistics and water poisoning every step of the way. It is a magnificent feat of engineering, but it is ultimately a brute force approach. We are hammering the molecules into compliance.
It is energy-intensive and capital-intensive, which naturally leads researchers to ask if there is a completely different path.
Exactly. What if we could step entirely outside those thermodynamic rules? What if we could bypass traditional thermal chemistry furnaces and boiling wax entirely and use alternative, exotic forms of energy to activate the methane? And that leads us straight into Chapter 3, plasma, microwave, and non-conventional reactors. The big idea here is using electrical energy, not bulk heat, to surgically break these bonds.
This is where the chemistry shifts heavily into the realm of high-energy physics. The core concept explored here is the use of non-equilibrium plasma reactors. These devices utilize highly targeted electrical energy, rather than bulk thermal heat, to excite electrons and physically shatter methane's carbon-hydrogen bonds at surprisingly low overall temperatures.
Those temperatures?
Yes. It offers a radical, physics-based alternative to the traditional giant SMR furnaces.
Okay, let's really dive into this, because the terminology can be misleading. When the average person hears the word plasma, they immediately think of the surface of the sun, or lightning bolts, or a welder's arc.
Right.
Extremely hot, destructive, uncontrollable stuff. But you just used the phrase low overall temperatures. How on earth does a plasma reactor break molecular bonds without instantly melting the stainless steel pipes it is built out of?
The key is distinguishing between a thermal equilibrium plasma and a non-equilibrium plasma. The examples you gave, star and arc welder. Those are thermal equilibrium plasmas. In those environments, everything is hot. The electrons are hot, the gas molecules are hot, the ions are hot. The thermal energy is distributed equally across all the mass, resulting in temperatures of thousands or millions of degrees.
Which would obviously melt any industrial reactor.
Precisely. But the symposium text discusses alternating current and direct current non-equilibrium plasmas. In these specific types of reactors, you take your cold methane gas and you pass it through a very strong, highly oscillating electric field. Instead of putting a massive fire under a vat to heat the entire bulk volume of the gas to 1,000 degrees, the electric field acts almost exclusively on the electrons.
Because the electrons have virtually zero mass compared to the rest of the atom, and they carry a negative electrical charge, the voltage field can grab them and whip them up to immense speeds almost instantly.
That is the exact mechanism. The strong electric field accelerates the free electrons to tremendous kinetic energies. These hyper-energetic electrons then act like a swarm of microscopic high-speed bullets. They fly through the reactor and slam violently into the relatively massive, cold, slow-moving methane molecules.
It's kinetic impact, not thermal melting.
Yes. The physical impact of the electron bullet transfers a massive amount of kinetic energy directly into the molecular structure of the methane. It causes instant dissociation and ionization. It literally knocks the hydrogen atoms right off the central carbon atom, instantly creating highly reactive molecular fragments, or free radicals.
And because the actual mass of the electrons is so infinitesimally small, even though they are moving at blistering speeds, they don't hold enough total thermal energy to heat up the bulk gas.
Right.
So the actual gas, the stuff you would physically feel if you could safely stick your hand inside the reactor, remains relatively cool, maybe just a bit warm to the touch.
Precisely. You are entirely bypassing the thermodynamic requirement to burn fuel for heat. You are substituting uniform thermal energy with highly targeted kinetic electron impacts to initiate the bond-breaking chemistry.
That is amazing.
What's fascinating here is what you can actually synthesize with this method. In our discussion of traditional SMR and Fischer-Tropsch, the entire agonizing goal was to make syngas first, and then spend billions turning that syngas into liquids.
Yeah, that was the whole point.
But the source material shows that with a targeted DC plasma reactor, you can skip the syngas intermediate entirely.
Wait, really?
Yes. You don't even need the oxygen. You can take pure methane and smash it directly into C2 hydrocarbons molecules with 2 carbon atoms, like acetylene, ethylene, and ethane.
It is a remarkable, elegant shortcut. By avoiding the introduction of oxygen entirely, you eliminate the constant, terrifying risk of the methane undergoing total combustion and turning into useless carbon dioxide.
Exactly.
When the plasma's electron bullets shatter the methane, they primarily create methyl radicals, a carbon atom with 3 hydrogens. These radicals immediately seek stability. They find each other in the cold gas, bind together, and instantly form 2 carbon chains. The data shows that acetylene is often the primary stable product formed because its triple carbon bond is thermodynamically favored at those highly localized, high-energy impact sites.
That is a massive scientific win. But from an industrial perspective, it presents a new problem.
Of course it does.
The global commodity market doesn't really want millions of tons of acetylene. Acetylene is primarily used for welding torches. The global chemical market is absolutely desperate, however, for ethylene. Ethylene is the most produced organic compound in the world.
Right. It's the precursor to polyethylene. It is the plastic water bottle, the grocery bag, the medical tubing, the insulation on your house wiring.
Everything.
So if the plasma reactor naturally makes acetylene, how do we tweak it to get ethylene instead? And the text outlines this brilliant, almost surgically precise mechanical detail.
Yes, the concept of in situ hydrogenation.
Mm-hmm.
The research teams realized that while the plasma naturally produces a high concentration of acetylene, the electron impacts are simultaneously knocking off huge amounts of pure, free hydrogen gas from the original methane.
Okay.
So the reactor is full of acetylene and free hydrogen. To take advantage of this, they physically placed a highly specific solid catalyst, a palladium-Y zeolite, directly inside the plasma reactor's electrical discharge zone.
They literally put the physical metal catalyst inside the microscopic lightning storm.
Exactly. And they maintain the overall bulk temperature of the reactor at a very cool 50 degrees Celsius.
Just 50 degrees.
Just 50. Here is what happens dynamically. As the plasma arcs generate the acetylene molecule, the palladium metal housed within the zeolite's microscopic pores immediately captures it. The palladium then grabs the free hydrogen that is floating around from the plasma fragmentation, and it catalytically, selectively hydrogenates the acetylene, adding exactly 2 hydrogen atoms to it, converting it into highly valuable ethylene right there on the spot.
And the temperature control is the key, right?
Yes, the low temperature is critical. If the bulk temperature gets too high, say 100 degrees Celsius, the palladium catalyst becomes too active. It will overhydrogenate the molecule, adding 4 hydrogens instead of 2, turning the valuable ethylene into completely useless ethane gas. But by holding the plasma environment precisely at 50 degrees, the physical structure of the zeolite and the chemistry of the palladium provide a beautiful real-time tuning of the product.
I love that concept. You are using the brute force physics of a high-voltage plasma to violently smash the molecule apart, but then you are using the elegant chemistry of a zeolite pore to gently catch the pieces and delicately shape them into the exact plastic precursor you want before they can escape.
It's very elegant.
But I do have to ask the practical question about industrial scalability. Usually when you read about these incredible glowing plasma experiments in scientific papers, they require massive, expensive vacuum pumps to operate at very low pressures to keep the plasma stable. You can't run a multi-billion-dollar industrial chemical plant on a fragile vacuum system.
No, you can't. That requirement for low pressure has historically been the primary barrier to commercializing plasma chemistry. But the symposium details a significant breakthrough: the development of a novel, self-designed metal initiator specifically used in microwave-induced plasma.
Metal initiator.
Yes. This specific, finely tuned metal antenna acts as a focal point for the microwave radiation. It allows the engineers to cleanly strike and dynamically maintain a perfectly stable, continuous, non-equilibrium plasma discharge under ambient room temperatures and, crucially, under normal atmospheric pressure.
It completely removes the need for the expensive, fragile vacuum technology.
Exactly. It brings this radical physics out of the specialized laboratory and inches it much closer to the heavy, rugged realities of an industrial refinery floor. However, even at atmospheric pressure, there are significant hurdles regarding the background gas composition. The text notes that the presence of diluting gases drastically alters the plasma chemistry.
How so?
Well, if you add extra hydrogen to the plasma, it acts as a stabilizing agent and physically prevents solid carbon coke from forming and destroying the reactor electrodes. But if you try to use an inert gas like argon to stabilize the plasma, the argon atoms actually undergo energy transfer collisions that enhance deep dehydrogenation, stripping all the hydrogen off and causing massive, instantaneous carbon coking.
So even with the physics dialed in, the chemistry of the gas mixture can still ruin the reactor. Let's do a quick practical recap of this section. Plasma uses electron collisions instead of heat. Coupling it with a zeolite lets you tune the product, like making ethylene. And diluting gases, matter hydrogen stops coke, argon causes it.
Spot on.
And for a critical thinking challenge here, if plasma reactors operate at low bulk temperatures, what are the primary energy efficiency losses that might prevent them from competing with thermal partial oxidation? Something to think about.
Definitely.
But this entire concept of non-equilibrium plasmas relies on using electricity to bypass the need for massive thermal furnaces. It's a high-voltage solution. But chemical researchers have another entirely different trick up their sleeves for achieving low-temperature methane conversion.
They do.
Instead of using the brute force of a high-speed electron bullet, they try to use the absolute surgical precision of complex organometallic chemistry. They rely on molecular elegance. And that takes us directly into Chapter 4. Low-temperature routes and organoplatinum chemistry. The big idea here is using platinum complexes to directly oxidize methane to methanol without high heat, but thermodynamics makes it incredibly tough.
The foundational concept here is incredibly tantalizing to chemists. The ultimate goal is the direct, single-step, low-temperature oxidation of methane gas directly into liquid methanol, using highly specialized organoplatinum complexes.
Single step.
Yes. On paper, it represents absolute theoretical perfection. It skips syngas, it skips massive heat, it skips high voltage. But in reality, it is currently blocked by massive thermodynamic hurdles because the desired end product, the liquid methanol, is significantly more chemically reactive than the starting methane gas.
Let's really drill down into this because this concept of the thermodynamic trap is fundamental to understanding why natural gas is so hard to work with. I want to set the stage with a visual analogy.
Go for it.
Methane, chemically speaking, is an incredibly tough nut to crack. The bonds holding the 4 hydrogen atoms to the central carbon atom are exceptionally strong and stable. Imagine you have a tough, stale piece of bread, and you are trying to lightly toast it using a military-grade flamethrower.
A slightly extreme visual, but thermodynamically accurate.
Because the bread is tough, it takes a second of blasting it with the flamethrower before the crust finally catches fire. But the instant you crack that outer barrier, the instant the bread starts to burn, it becomes highly vulnerable. It goes from slightly toasted to completely incinerated ash in a fraction of a second. In chemistry, methane is that tough bread. But once you finally manage to crack a carbon-hydrogen bond and slip a single oxygen atom in there to create liquid methanol, that new methanol molecule is much, much easier to burn than the methane ever was.
That is the exact trap, articulated perfectly. Methane fiercely resists reacting. But the instant it becomes methanol, the molecule becomes eager, almost desperate to react further. And because traditional high-temperature processes, like the partial oxidation we discussed earlier, rely on violently reactive, chaotic free radicals flying around, those radicals do not care what they hit.
Right.
They have no selectivity. They will ignore the tough, unreacted methane molecules floating around, and they will continuously, aggressively attack the newly formed fragile methanol molecules. The chemical reaction naturally cascades out of control. It just keeps burning the methanol all the way down to carbon dioxide and water. So you might successfully process a massive amount of methane through your reactor, but your actual liquid yield of methanol at the end of the pipe stays devastatingly near zero because it all burned up the millisecond it was formed.
So the lesson is, if high heat and chaotic free radicals inherently destroy our valuable product, we have to go cold. We have to abandon the flamethrower and use a microscopic sniper rifle. And the text spends a great deal of time discussing the Shilov system, What exactly is the Shiloh system?
The Shiloh system was actually developed decades ago by A.E. Shiloh, and it represents a masterclass in organometallic chemistry. It uses aqueous platinum specifically, complex molecules containing platinum-2 and platinum-4 ions that are dissolved in a water solution. The entire system operates at incredibly low temperatures, roughly 100 degrees Celsius, completely avoiding the 1,000-degree infernos of standard reactors. It operates via a highly specific mechanism called electrophilic activation.
Okay, let's freeze right there. Electrophilic activation is heavy jargon. What is the platinum atom actually doing to the electrons in the methane molecule? How does it break the bond without using heat or plasma?
It comes down to the electron orbitals of the transition metal. The platinum-2 atom in the solution acts as your molecular sniper. It is electrophilic, meaning it is electron-loving. It has empty d orbitals that are hungry for electrons.
Okay, it wants electrons.
Right. As a methane molecule floats by in the solution, the platinum-2 atom specifically targets the dense cloud of electrons forming one of the carbon-hydrogen bonds. It physically coordinates with the methane molecule, gently drawing the electrons of the CH bond into its own empty orbitals. By pulling those electrons away, it gracefully weakens and breaks the bond between the carbon and the hydrogen without ever creating a chaotic free radical.
It essentially puts the methane molecule in a highly controlled protective molecular headlock.
Exactly. It forms a highly stable metal-carbon bond, creating what we call a methyl-platinum intermediate. The tough methane has been cracked, but the resulting piece is held firmly and safely by the platinum atom.
And then what? How do we get the oxygen in there to make methanol?
Once the methyl group is safely secured by the platinum-2, the second component of the system, the platinum-4 complex, acts as the oxidant. Because platinum-4 is in a higher oxidation state, it aggressively attacks that methyl-platinum intermediate. It forces the methyl group to accept an oxygen atom derived from the water, releasing the final product as liquid methanol. In the process, the platinum-4 is reduced, and the original platinum-2 atom is left completely intact, ready to catch another passing methane molecule.
Oh, that's beautiful.
It's a beautifully choreographed molecular dance that bypasses the free radical chaos entirely.
The symposium text also points out another incredibly successful variation of this low-temperature approach, using concentrated sulfuric acid as the solvent instead of water, alongside a platinum complex. The researchers report an astonishing conversion yield of over 70%.
It's just huge.
But here's the trick. They don't actually make raw methanol. They convert the methane into a different molecule called methyl bisulfate. Why is that specific reaction yield 70% when making raw methanol yields almost nothing?
It goes back to the flamethrower analogy. It is entirely about protecting the product. When you react methane in concentrated sulfuric acid with this specific platinum catalyst, the chemistry dictates that you don't form fragile methanol. You form methyl bisulfate. Remember the thermodynamic trap. Methanol is highly reactive and burns instantly. But methyl bisulfate is chemically unique. Its electron structure actually makes it less reactive than the original methane gas.
So the methyl bisulfate acts like a heavy fireproof jacket around the carbon atom.
That is the perfect way to visualize it. Once the methane is successfully converted into methyl bisulfate, it becomes thermodynamically armored. It is totally protected from any further oxidation by the acid or the catalyst. You can achieve massive 70% yields in the reactor because the product simply sits there, perfectly safe and stable, accumulating in the fluid.
That is so smart.
Once you extract the methyl bisulfate from the reactor, you can take to a separate controlled environment and gently hydrolyze it. React it with water to strip off the bisulfate and yield your pure liquid methanol.
Okay, so this is where I have to step back and look at the big picture. You are telling me we have a chemical system that achieves a 70% conversion yield at low temperatures. We have successfully beaten the thermodynamic trap that has plagued the industry for a century. So what does this all mean? Why aren't massive energy conglomerates like ExxonMobil and BP building these organoplatinum sulfuric acid plants on every street corner? What is the catch that keeps this in the laboratory?
The catch is a brutal economic reality known as the bottleneck of stoichiometry. In both the original aqueous Shiloh system and the high-yield sulfuric acid system, the platinum oxidant, the platinum-4, is physically chemically consumed during the final step of releasing the product. It gives up its oxidative power and becomes useless.
And platinum is one of the rarest, most expensive precious metals on the entire planet. You can't just consume tons of it every day to make cheap fuel.
Precisely. To make any of these low-temperature molecular architectures economically viable on a massive industrial scale, the system cannot be stoichiometric. It must be fully catalytic. You need to be able to use a cheap, infinitely plentiful secondary oxidant, specifically elemental oxygen pulled straight from the ambient air, to constantly reoxidize and recycle the dead platinum back into platinum-4 so it can be used millions of times.
And we simply don't know how to do that yet.
It remains deeply, intensely challenging. The problem is the organic ligands, the complex molecular scaffolding that chemists build around the platinum atom to make it soluble in the acid and tune its reactivity. If you bubble pure oxygen gas from the air into that hot acid mixture to regenerate the platinum, the oxygen doesn't just quietly regenerate the metal.
Let me guess, it burns it.
It violently, blindly attacks and combusts the delicate organic ligands holding the catalyst together. The catalyst literally burns itself to pieces, designing a molecular architecture that is robust enough to split elemental oxygen from the air, funnel that oxidative power directly into the platinum atom, and completely ignore the surrounding organic scaffolding, is a Nobel Prize-level challenge that is still being fiercely researched today.
Let's do a quick practical recap of this chapter. High heat causes chaotic free radicals that burn our product. Platinum complexes let us activate the bonds at low temperatures, gently, and protecting the product, like turning it into methyl bisulfate instead of raw methanol, is the only way to get high yields.
That's the essence of it.
And for a critical thinking challenge, if a commercially viable organoplatinum catalyst is developed, how would it disrupt the global supply chain currently dominated by multi-billion-dollar syngas and Fischer-Tropsch facilities? It would be a total game changer.
It would rewrite the entire industry overnight.
Which perfectly frames the macroeconomic reality of the energy sector. The academic chemists and the quantum physicists are hunting for the perfect, elegant, low-temperature platinum catalyst or the perfectly tuned microwave plasma reactor. And it is beautiful, paradigm-shifting science. But the global energy industry cannot wait for absolute perfection.
They really can't.
They have trillions of cubic feet of stranded natural gas that is bleeding financial value every single day it sits in the ground. They must monetize it right now, today, using the heavy, imperfect, brute force thermal tools they already possess. And that tension forces us to look at the massive global strategies of what the industry calls the natural gas refinery. And that is Chapter 5, our final major theme of the symposium text.
It is the ultimate synthesis of all the chemistry we have discussed.
The big idea here is that the future isn't just synthesizing diesel replacements, it's the natural gas refinery model, producing specialized oxygenates like DME for power generation.
Right. The core idea presented in the later chapters is that the future of natural gas conversion isn't solely focused on synthesizing direct drop-in replacements for crude oil products, like synthetic diesel, because that is a financially dangerous game. Instead, the industry is shifting toward a natural gas refinery model, aiming to use syngas to produce massive quantities of specialized, high-value oxygenates, specifically a chemical called dimethyl ether, or DME, for use in clean power generation and heavy transport.
Let's set the economic baseline for this pivot. Because for the entire discussion of Fischer-Tropsch, we assumed the absolute holy grail was making synthetic diesel fuel for trucks. Why change the target product? Why give up on diesel?
It comes down to the brutal realities of scale and global commodity markets. Currently, a massive amount of natural gas, about 4 trillion cubic feet per year, is converted chemically. We mostly turn into ammonia for global agricultural fertilizer and into methanol for plastics. 4 trillion cubic feet sounds like a massive number, but it actually represents only about 5% of total global natural gas consumption.
Just 5%.
Just 5. The vast, overwhelming majority of stranded gas, sitting deep in the reserves in Alaska, or offshore Trinidad, or in the Middle East, is still waiting to be monetized.
And if you spend $5 billion building an incredible state-of-the-art Fischer-Tropsch GTL plant in the desert simply to make synthetic diesel, what happens?
What happens is you are putting your highly engineered, incredibly expensive synthetic product into direct, brutal commodity competition with standard diesel that is cheaply refined by simply boiling crude oil. The profit margins of your multi-billion-dollar GTL plant are entirely handcuffed to the geopolitical price of a barrel of crude oil.
Right.
If OPEC floods the market and the price of crude oil drops dramatically, the standard refineries can sell diesel for pennies, and your high-tech GTL plant instantly starts hemorrhaging money. It becomes a stranded asset.
So from a corporate risk perspective, you need a product that has its own distinct high-value market, separate from the wild roller coaster of crude oil prices. And you mentioned BP's intense push, documented in the text, toward oxygenates, specifically DME. What exactly is dimethyl ether?
DME is a relatively simple molecule, easily synthesized from the carbon monoxide and hydrogen in our syngas. It is essentially two methyl groups joined by a single oxygen atom in the center. Historically, for decades, it was just used as a benign, non-toxic aerosol propellant in consumer hairspray.
Hairspray.
Yeah. But from an energy density standpoint, it has incredible combustion properties. It is a gas at room temperature, but it liquefies at very moderate pressures, much like the propane in a backyard grill. This makes it incredibly easy and cheap to transport in standard pressurized steel tanks. And because it contains that oxygen atom in its chemical structure, it burns exceptionally cleanly, with virtually zero black soot or particulate matter.
That makes it a great clean-burning substitute for diesel fuel and heavy trucks. But the text outlines testing DME for something much, much bigger. BP and EPDC in Japan ran extensive engineering tests firing DME not just in trucks, but in massive, heavy-duty industrial gas turbines designed for grid-scale power generation.
This raises an important question, though.
Exactly. Why on earth would you spend billions of dollars to take natural gas, tear it apart into syngas, stitch it back together into liquid DME, ship it across the ocean, only to vaporize it and burn it in a massive gas turbine to generate electricity? Why not just pipe the natural gas straight into the turbine in the first place?
Because of simple geography. In massive, energy-hungry economies like Japan or vast parts of Western Europe, they simply do not have domestic natural gas reserves. They cannot build a pipeline to a gas field because the gas field is an ocean away. They are entirely dependent on importing energy as liquefied natural gas, or LNG.
And we know how expensive that is.
Extremely.
Yeah.
As we discussed at the very beginning, LNG requires multi-billion-dollar cryogenic freezing infrastructure at the export terminal to turn the gas into a liquid at negative 260 degrees. And it requires equally expensive cryogenic regasification terminals at the receiving port to warm it back up.
Yeah.
It is a massively expensive, highly complex supply chain.
So the BP tests were aiming to see if DME could completely bypass the cryogenic LNG supply chain.
Exactly. And the engineering test proved to be a massive success. They demonstrated that DME can be fired in modern heavy-duty gas turbines with only minor, inexpensive modifications to the fuel delivery systems. It offered lower heat rates, higher equipment availability due to lack of soot, and emissions that were comparable to, or even cleaner than, burning pure, unrefined natural gas.
The economic implications of that are staggering. You can build your natural gas refinery right at the remote gas field. You convert the untransportable stranded gas into liquid DME using moderate pressure. You load that liquid DME onto standard, cheap, pressurized LPG tankers, which cost a fraction of what a highly specialized cryogenic LNG tanker costs.
Right.
You ship it to Japan, plug it directly into their power grid, and you completely sidestep both the crude oil market and the cryogenic LNG market. And you have created a parallel energy economy.
It is a brilliant logistical strategy, but it still faces one monumental hurdle. Making the DME still requires making the syngas first. And as we established an hour ago, generating the syngas accounts for 60% of the total plant cost. If you can't drastically lower the cost of making the syngas, the DME will never be cheap enough to compete with imported coal or LNG.
So how are the chemical engineers fixing the economics of the syngas step for these mega refineries?
By aggressively attacking the cost of oxygen. Throughout this discussion, when we talked about the highly efficient advanced reactors like autothermal reforming and partial oxidation, we noted that they require a feed of pure oxygen gas, not ambient air.
Why can't we just blow air into the reactor? Air is free. Oxygen is everywhere.
Air is free, but air is also 78% inert nitrogen gas. If you blow raw air into a partial oxidation reactor, that massive volume of nitrogen does absolutely nothing chemically. It just takes up space.
Ah, I see.
It physically inflates the required size of all your downstream pipes, all your compressors, and your Fischer-Tropsch reactors. You have to build the entire multi-billion-dollar plant 4 times larger just to accommodate the useless nitrogen passing through it. That ruins the economics instantly. So you have to separate the oxygen from the air before you feed it to the reactor. You have to build an air separation unit, an ASU.
And an ASU on an industrial scale is essentially a gigantic, power-hungry refrigerator that cryogenically cools massive volumes of ambient air until the oxygen literally condenses into a liquid, allowing you to distill it away from the nitrogen. They are massively expensive to build, and they consume huge amounts of the electricity the plant generates.
Precisely. They are an economic albatross. But the symposium text details a potential technological breakthrough that could change everything. The development of dense ceramic oxygen transport membranes, or OTMs.
Explain how a ceramic membrane works. I picture a ceramic coffee mug. It's completely solid. How does gas pass through it?
It relies on advanced solid-state chemistry. Imagine building the physical wall of your syngas reactor, not out of steel, but out of a specialized advanced perovskite ceramic material. On the outside of the reactor wall, you flow hot, pressurized ambient air. On the inside of the reactor, you flow your methane gas. At very high temperatures, around 900 degrees Celsius, the crystalline lattice structure of this specific ceramic becomes mobile. It develops highly specific atomic vacancies.
So the solid wall acts as a molecular filter.
More than a filter, it acts as an active chemical pump. The extreme heat causes the oxygen molecules in the air on the outside to dissociate into individual oxygen ions. The pressure gradient forces those specific oxygen ions to physically migrate through the microscopic vacancies in the solid ceramic lattice.
It pulls them right through the solid wall.
Yes, it physically rips the oxygen from the air, leaves the useless nitrogen behind on the outside, and pulls only the pure oxygen ions through the solid wall, where they immediately react with the methane on the inside to form syngas.
It extracts pure elemental oxygen from the ambient air seamlessly without moving parts right at the exact atomic moment of reaction.
Exactly. It is elegant, solid-state chemistry. And if it can be successfully scaled up to withstand the massive pressures of an industrial plant without the ceramic cracking, it completely eliminates the need to build the massive billion-dollar cryogenic air separation unit.
Wow.
The engineering estimates presented in the text suggest that successfully integrating OTMs into the syngas process could slash the total capital costs of gas-to-liquids plant by a staggering 20 to 50%.
Slashing the capital cost by half. Let's do a quick practical recap of this final chapter. The focus is shifting to oxygenates like DME. DME is amazing for power generation and skips the whole cryogenic LNG nightmare. And the key to making it affordable is eliminating those cryogenic air separation units using ceramic membranes.
That's the playbook.
And a critical thinking challenge for you. If DME becomes a dominant fuel, what infrastructural changes are actually required globally to transport and store it compared to LNG?
It's a massive logistical question.
That single technological leap replacing a giant refrigerator with a smart ceramic wall is what makes the natural gas refinery economically dominant over crude oil. It makes the entire DME power generation concept viable. It is amazing how the global flow of energy ultimately comes down to the behavior of oxygen ions migrating through a piece of hot ceramic.
It is a testament to the fact that the macroeconomics of the energy sector are entirely subservient to physical chemistry.
It really is. We have covered an immense amount of ground today, from the violent thermal shockwaves of millisecond reactors to the elegant, sniper-like precision of platinum catalysts to the global shipping logistics of dimethyl ether. But I want to leave you, the listener, with one final, incredibly provocative thought that weaves all of this together. We have spent this entire deep dive, an hour of intense atomic-level chemistry, talking about how to turn stubborn methane gas into various liquid fuels so that we can ultimately put them in a machine and burn them. Whether it is synthetic diesel combusting in a heavy truck or liquid DME combusting in a Japanese power plant, the end result of all this multi-billion-dollar engineering is combustion, which means the end result is breaking those carbon bonds to release energy, inevitably putting millions of tons of carbon dioxide into the atmosphere. But there's one final, mind-bending concept briefly explored in the source text regarding something called methane decomposition.
It is a concept that entirely flips the fossil fuel paradigm on its head.
Exactly. Think about the chemistry we just discussed. What if we stop trying to add oxygen? What if we don't make syngas at all? The text explores what happens if you take a specialized catalyst, apply targeted thermal or plasma energy, and simply strip the 4 hydrogen atoms entirely off the central carbon atom in methane. You don't burn it, you just fracture it. The result: you get a stream of pure carbon monoxide-free hydrogen gas. Hydrogen gas is the ultimate zero-emission fuel for next-generation hydrogen fuel cell vehicles. When you burn hydrogen, the only exhaust product is pure water vapor.
And the byproduct of this decomposition process.
The byproduct is the central carbon atom itself, stripped of its hydrogen. It falls out of the gas stream as solid carbon. Pure graphite, carbon black.
Which is not a greenhouse gas. It is a highly valuable physical solid.
Exactly. It is a solid material that can be used to manufacture physical goods. It can be used to make advanced plastics, ultra-strong carbon fiber composites for aerospace, structural components for building materials, and additives for tires. Imagine that future. I challenge you to imagine a world where natural gas is no longer viewed by society as a dirty fossil fuel that inevitably contributes to the greenhouse effect. Instead, it becomes a permanent, highly valuable carbon sequestering feedstock. We pull the gas from the earth, we strip off the hydrogen to power our clean cities, and we use the remaining solid carbon to physically build the infrastructure of our civilization. It leaves behind clean energy as its only energetic byproduct and locks the carbon away in our buildings and cars forever.
It is a profound shift in perspective. It redefines the purpose of the global extraction industry entirely.
We want to thank you for joining us on this incredibly intense deep dive today. We hope that the next time you turn on the blue flame of your kitchen stovetop or see footage of a flare stack burning in the distance, you don't just see simple fire. We hope you see the complex, delicate, and immensely powerful dance of thermodynamics, the incredible potential of molecular catalysis, and the ongoing, brilliant battle by engineers to harness the fundamental building blocks of our world. Until next time, keep exploring.